Have you ever paused to consider just how fragile our grasp on reality truly is? Not so long ago, we believed with absolute certainty that the Earth sat motionless at the very center of the universe. Then, almost overnight in the grand scale of history, we discovered ourselves hurtling through the void, orbiting a star that is merely one among billions. This was only the beginning of a long journey of disillusionment and discovery. From the faint whispers found in the cosmic microwave background to the fleeting brilliance of fast radio bursts, every new marvel has forced us to tear up the rulebook of existence. We find ourselves walking in the footsteps of bold thinkers and meticulous observers who dared to confront the prevailing wisdom of their time, often at a great personal cost. From the fierce debates surrounding the origins of the Big Bang to the eerie, unexplained dimming of distant stars that still baffles modern science, these stories serve as a powerful reminder: the universe is far stranger than we dare to imagine, and our most cherished truths may one day be overturned. It is a long story, one perhaps best suited for the world of dreams, but before we begin, remember to engage with our journey. For thousands of years, the stillness of the earth was the cornerstone of human understanding, a pillar of philosophy, religion, and certainty itself from ancient Greece through the Middle Ages. But then, the tide began to turn with a quiet man from Poland named Nicolaus Copernicus, who harbored an idea that would alter the course of human history. Copernicus was a man of many roles: mathematician, astronomer, and church official, deeply educated and sincerely devout. The initial reaction was slow, as many scholars viewed his work as a mere mathematical tool rather than a physical reality. However, the atmosphere shifted when others began to take the heliocentric idea seriously, most notably Galileo Galilei. Using one of the earliest telescopes, Galileo saw things that had never been seen before. He witnessed moons orbiting Jupiter, proving that not everything in the heavens revolved around the Earth. He observed the phases of Venus, a phenomenon that could only be explained if Venus orbited the Sun. Galileo was bold. He didn't just whisper these findings in academic circles but wrote for the common person in Italian rather than Latin, insisting that this model was the literal truth. This brought him into direct conflict with the authorities. In 1616, the Church officially declared heliocentrism heretical. Galileo was warned to stop, and for a time, he remained silent. But in 1632, he published his dialogue concerning the two chief world systems. Though framed as a conversation, it clearly favored the Copernican view and even seemed to mock those who clung to the old ways. The response was swift. Galileo was summoned to Rome, forced under extreme pressure to recant his beliefs, and sentenced to house arrest for the rest of his life. Despite this, the crack in the old world order had been made. Copernicus started it, Galileo continued it, and the profound shaking of human self-perception could not be undone. As time moved forward, thinkers like Johannes Kepler and Isaac Newton transformed the universe from a theological mystery into a measurable, predictable machine governed by the laws of motion and universal gravitation. Yet the path to this understanding was long and fraught with peril. The shift from a geocentric to a heliocentric world was one of the most significant turning points in history. It was the moment we began to look outward not with fear, but with curiosity. By the early 20th century, our horizon expanded once more. Most astronomers still believed the Milky Way was the entire universe, a lone island of stars in an empty void. The strange, fuzzy patches in the sky known as nebulae were thought to be mere clouds of gas within our own galaxy. This led to the great debate of 1920 between Harlow Shapley and Heber Curtis. Shapley argued the Milky Way was vast and encompassed everything we saw, while Curtis maintained that these spiral nebulae were actually island universes, entire galaxies far beyond our own. The debate remained unsettled until 1923, when Edwin Hubble pointed the world's most powerful telescope at the Andromeda Nebula and identified Cepheid variable stars. This discovery proved once and for all that Andromeda was a separate galaxy, millions of light-years away. In that single moment, the universe became unimaginably larger, and we realized that we are but a small part of a vast, expanding cosmic sea. Through the power of a formidable lens at Mount Wilson, a discovery was made that would shatter the boundaries of our known world. By identifying a Cepheid variable star within what was then called the Andromeda Nebula, Edwin Hubble applied the established methods of distance measurement and arrived at a staggering conclusion: Andromeda was not a mere cloud of gas within our own galaxy, but an entire island universe situated over 2 million light-years away. Almost overnight, the cosmos expanded. The great debate was effectively settled, paving the way for a new reality where the universe was populated by countless galaxies, all drifting far beyond the reaches of the Milky Way. This shift marked our transition from a familiar, static neighborhood into the vast, expanding expanse we study today. Science often progresses not through sudden leaps, but through the steady accumulation of evidence and the rigorous clashing of ideas. Without the technological leap of the 100-inch Hooker telescope, the stars within Andromeda would have remained hidden, just as the moons of Jupiter remained invisible before Galileo. Where people once looked up and saw mystery, they now began to see structure, distance, and a scale that defied the human imagination. By the late 1920s, Hubble pushed even further, analyzing the light from these distant galaxies through a prism to reveal their spectra. He noticed a peculiar phenomenon: the spectral lines, which serve as chemical fingerprints of the stars, were systematically shifted toward the red end of the spectrum. This redshift carried a profound physical implication. Just as the pitch of a siren drops as it moves away from you, the light from these galaxies was stretching as they retreated. Hubble discovered a definitive relationship: the farther a galaxy was, the faster it appeared to be moving away. This wasn't just galaxies drifting through space, it was space itself stretching in every direction, like the surface of an inflating balloon. The idea of a static, eternal universe, a cosmic clockwork that had persisted since the time of Newton, was dead. If the universe was expanding, it implied a beginning, a moment in the distant past when everything was condensed into a single, infinitesimal point. This was the birth of the Big Bang Theory, a concept that many, including Albert Einstein, initially resisted, but which the overwhelming data eventually forced them to accept. The next great piece of the puzzle fell into place by accident in the early 1960s. Two engineers, Arno Penzias and Robert Wilson, were troubled by a persistent background hiss in their radio antenna that they couldn't explain. No matter where they pointed their instrument, the noise remained steady, uniform, and coming from every corner of the sky. After exhausting every possible terrestrial explanation, they realized they had stumbled upon the afterglow of the creation of the universe. This cosmic microwave background radiation was the fading heat of the Big Bang, cooled over billions of years to just a few degrees above absolute zero. This discovery provided the definitive evidence that the universe had a hot, dense beginning, effectively silencing the steady-state model championed by Fred Hoyle. Hoyle had famously coined the term Big Bang as a dismissal on a radio program, preferring a universe that was eternal and unchanging. Yet, the data from the heavens told a different story. The universe was not only expanding but was also a relic of a singular, explosive event. As our instruments grew more sophisticated, specifically with the launch of satellites like Cope and Planck, we began to see that this background radiation wasn't perfectly smooth. It contained tiny fluctuations in temperature, the seeds of future galaxies. These wrinkles in the early universe allowed us to read the age, shape, and composition of the cosmos with unprecedented precision. We began to understand how much of the universe is made of ordinary matter and how much is hidden. However, this sense of order was soon challenged once more. In the 1970s, Vera Rubin observed that the stars at the outer edges of spiral galaxies were rotating far faster than the visible matter should allow. According to the laws of gravity, these stars should have been flung out into the void, yet they remain tightly bound. This discrepancy suggested that there is a vast amount of invisible dark matter providing the necessary gravitational glue. Once again, the universe proved to be larger, older, and far stranger than we ever anticipated, reminding us that every time we think we have mastered the rules of existence, the cosmos reveals a deeper mystery yet to be solved. The stars in the outer reaches of spiral galaxies seem to be held by an invisible hand, caught in a gravitational grip that our traditional models simply cannot explain. When Vera Rubin meticulously studied dozens of galaxies in the 1970s, she discovered a consistent and startling pattern. The stars at the far edges were rotating just as fast as those near the center. According to the laws established by Newton, these outer stars should have slowed down as gravity weakened with distance. Instead, they raced along, suggesting that either our understanding of gravity is flawed on a galactic scale, or there exists a vast amount of matter that we simply cannot see. This invisible mass, which exerts a powerful pull but refuses to emit or reflect light, needed a name. Astronomers called it dark matter. While the term had been used decades earlier by Fritz Zwicky to explain the frantic movement of galaxies within clusters, it was Rubin's precise data that turned a fringe observation into a fundamental pillar of astrophysics. This dark matter is not merely a placeholder for the unknown, it is a ghost-like substance that does not interact with light, yet it acts as the gravitational glue holding the cosmic web together. Without it, galaxies would never have formed, and the universe as we know it would lack the structure required for life to emerge. As we peer deeper into the history of the cosmos, we encounter objects that seem to defy time itself. In our own Milky Way, there is a star known as the Methuselah star, whose age once appeared to challenge the very birth of the universe. Initial measurements suggested the star was older than the estimated age of the cosmos derived from the Big Bang. While further refinements and an understanding of its low metal content have brought these numbers closer together, the tension remains a vivid reminder of how delicate our cosmic clocks truly are. It forces us to ask whether our models of stellar evolution are complete, or if the expansion rate of the universe hides a deeper mystery. This star stands at the crossroads of a larger debate, where different methods of measuring the universe's age yield conflicting results, suggesting that our understanding of time on a grand scale may still be missing a crucial piece of the puzzle. In the realm of theoretical physics, the equations that give us black holes also hint at their polar opposites, white holes. If a black hole is an inescapable trap where everything enters and nothing leaves, a white hole is a fountain of matter and light where nothing can ever enter. While black holes have transitioned from mathematical curiosities to observed realities that anchor the centers of galaxies, white holes remain on the edge of the imagination. They represent a perfect symmetry in the laws of physics, suggesting that time might be more flexible than we experience. Some theorists propose that white holes could be the exit points of black holes, a cosmic rebound where matter compressed to a singular point eventually erupts elsewhere in space or time. Although we have yet to find a single shred of observational evidence for their existence, white holes remain a daring possibility allowed by the rules of relativity, a mathematical rebellion waiting for the universe to decide if it belongs in reality. The journey toward understanding these extremes began with Albert Einstein's skepticism. He famously doubted that nature would ever allow a star to collapse into a point of infinite density, viewing such singularities as mathematical flaws rather than physical truths. Yet, as the 20th century progressed, the work of thinkers like Oppenheimer and later Hawking and Penrose proved that for massive stars, collapse is inevitable once their fuel is spent. Black holes evolved from a controversial theory into a cornerstone of modern science, confirmed by the intense X-rays of Cygnus X1 and the ripples of gravitational waves. Today, we know that the universe is not the smooth, continuous place Einstein once hoped for. It is a landscape torn, folded, and shaped by invisible structures. From the silent pull of dark matter to the violent edges of event horizons, the cosmos continues to prove that it is far wilder than we imagined, governed by laws that allow for both the birth of light and the absolute mastery of shadows. That concludes our journey. I hope these thoughts bring you peaceful dreams and a wonderful day ahead. We look forward to seeing you in our next episode.